Hello, Brian.
Hey, Adam.
How you doing?
Doing well. There's Aryan. And then Nathaniel, are you there?
I am.
And do you know if is Eric going to be able to join us? He said he was going to, but then I wasn't.
I think he will.
Yeah, okay.
He just responded in chat as though he's going to.
Oh, that's good. Yeah, just now? Or
Yeah.
Oh,
like
good. Yeah.
30 seconds ago.
Excellent. Alrighty. Yeah, I know we've got and I don't know if Matt was going to be able to join us. Matt Keeter.
I believe he was installing the app on his phone.
I think Robert might be doing the same. It's like, okay, look, I know it's very on brand for us to open all these spaces complaining about Twitter Spaces, but can we please make the desktop app allow you to speak in addition to listen? I get that. I know that's a totally separate code path, and this is like much more complicated than we can possibly imagine, but it is really annoying that people cannot join for the desktop.
Yeah, until they come up with a fix for that, Robert is coming in by way of my proxy, so you'll get 2 for the price of 1 on this one.
Wait, are we getting 2 voices, or is this going to be like Brian, Robert says?
Right, exactly.
It'll vary. It depends.
I don't like. This is really weird to be seeing Steve's avatar have Robert's voice. I'm not sure if I'm ready for this. I feel like I need.
You just have to deal with it. Sorry,
oh my god! Oh my god! This is. I think
now I don't know who's talking. It could be anyone telling Brian. Just
it's on brand for both of them, so it's very hard to know. All right. Well, and I'll be there. Is Matt, and then the I think Eric is the just waiting on Eric, but we can. All right. Well, we can get going here. Aryan, do you want to? There is Eric. Do you want to pick us up with? Actually, let me set the stage a little bit here because we were trying to pull off something so ridiculous that it's actually very hard to have a single Twitter space about it. We were doing the Bringup of the Sidecar switch, which we're going to be talking a lot about, and Aryan did a terrific Twitter space on the design of that. While we were doing that, we were also completing the Bringup of Gimlet, which was our compute sled, which we did a Twitter space on successfully being able to bring the SP3 out of reset. As it turns out, we definitely felt the wind was at the back, which was true, but we had some very serious adventures ahead of us when we last talked about Gimlet. So we were finishing up the Bringup of Gimlet and bring up all the components there. And then we also got a cameo from another board that we also did that we brought up in the middle of all of this, the PowerShell controller, which it fortunately ended up being that was much smaller. And then we're also trying to finish up trying to make the necessary revisions for the Rev 2 of our Gimlet schematics. So there's a whole lot of stuff going on, more or less at the same time, with not many more people than are here. Basically, the people that are speakers were the ones who were doing this. So it was an incredibly small team. Really exciting time. Aryan, I thought we might kick us off with you and I before the starting Bringup, which we're going to do in Emeryville, not Minnesota. I just remember us walking, kind of musing about the differences between Sidecar Bringup and Gimlet Bringup, and the things that were going to be that we felt would be more in hand, and then the things that we thought were going to be way more challenging. Do you want to maybe set the stage with that?
And while you do that, you might define some of those terms as we go. We've got lots of code names going on that the avid listener will recall, but we want to appeal to everyone.
Sure. So let's start with Gimlet, which is our compute node. It's an AMD EPYC-based server, with a NIC and NVMe drives in the front. So that was the board the team was already like in Bringup with. but we were struggling to get the AMD CPU out of reset, and then later some follow-up tales with a NIC. And then we have Sidecar, which is a board built around the Tofino 2 switching ASIC from Intel, which is a large like Ethernet switch capable of up to 12 terabits per second of throughput. And that thing does not have a host CPU on the board. We're connecting that using an external PCI Express cable to one of our compute nodes in the rack. And so one of the things that we were musing about was that, well, there's a lot of circuitry on this Sidecar board that we have sort of explored already once in Gimlet, because they share quite a bit of functionality, especially when it comes to board control. So there's a what we call the service processor, which is a CPU that, like an ARM CPU, that manages things like power supplies turning on and off, fans turning on and off, like all the sort of environmental pieces that you need in order to even start working with an ASIC or a large SoC. And so a bunch of that stuff was replicated to Sidecar. So we felt like, okay, that should be, pretty doable. We'll have that in hand because this is the second time we've seen it, and we've made some revisions that should help us get past the first hurdles that we encountered while we did the initial bring up of Gimlet. That turned out to be mostly true. We did not have significant issues that would get us stumped to basically power up all pieces and to sort of get the things out of reset. But then the Tofino 2 ASIC is a rather beefy device, requiring lots and lots and lots of power and a very tight envelope in which it needs to operate. And so that was going to be our main challenge. We felt to get the PDN. Well, to get the PDN to power up would have been fine. We had confidence that would work, but then to really keep it within the narrow operating range that it needs to operate in under load conditions for this ASIC, that was going to be a challenge.
And Aaron, you had a great Twitter thread earlier today that kind of expanded on this challenge. And Eric is here, who designed the PDN. Could you elaborate a little bit on why this is so challenging, like what a load step means, and why this load step was really gnarly?
Yes. So basically, when an ASIC turns on, or when an ASIC suddenly starts doing more work, more transistors start switching. Or they suddenly turn on, and during that process, an ASIC immediately draws a lot more current if the voltage stays the same. This is different to, for example, an AMD CPU or an Intel CPU, where they change the core voltage, so they step up the voltage in order to not need as much current to deliver the same amount of power through the device. This goes hand in hand with clocks that go up in frequency. That does not happen in a lot of these larger ASICs. So that might be happening in a GPU, but definitely in this networking ASIC, that is not true. Everything stays rather sort of fixed. But what that means is that once you apply power to this device and you then release the reset, it suddenly jumps by 300 amps in power. And that happens in the span of about a microsecond, and during that, and then because of how a PDN is designed on a circuit board, such a PDN can never instantaneously respond to a load step like that. It needs to sense that more current is required before the controller will apply, like basically allow more current through the power MOSFETs that it's driving. And so there's a slight lag behind, like as the PDN tries to catch up when the ASIC suddenly stomped on the accelerator, and as a result, the voltage will drop a little bit because of hand wavy inductance, and as current flows through the board. When that voltage drops, you need to stay above the absolute limit of the ASIC, because if that voltage drops below the limit, then you're going to get, best case, you're going to get errors, like bit errors, because transistors will not be switching in time, or worst case, you might have sort of things that might hang, like they might not switch completely, and so you might induce more current through these transistors, potentially causing higher currents that might damage the part. So there's a variety of different reasons why you do not want to have that voltage drop below the limit that is set for this part.
And that's the droop, right? I mean,
that is what is referred to as droop, yes. And then similarly, when the ASIC suddenly stops, like for example, when the ASIC has been going at full speed and you suddenly apply the reset again, suddenly all these transistors stop switching, and now there's this basically excess current that is underway because the PDN hasn't realized yet that it needs to step down the amount of current that is being released into the board. And now you get an overshoot because there's a similar effect on the way up, and that overshoot can potentially cause an overvoltage if that spike is sufficiently high that pushes you out of the upper limit, and that might now damage the part. So you have to operate within this narrow window, never undershoot and never overshoot too far, because otherwise your part is either not going to function properly or it might damage itself.
And when we first looked into this part, Arjen, I remember you just being wide-eyed about like, wow, this is going to be really hard to hit. And we were, very excited, Eric, when you came aboard as someone with a great deal of domain expertise. And Eric, I'd be curious, like, because what are the actual numbers in terms of the requirement for droop and overshoot for this part?
Yeah,
I want to say that I don't know how confidential the numbers are, so I've been a little bit vague.
I'll be approximate.
Yeah,
be approximate. But on these parts, you're running on these process nodes around 900 millivolts, 800 to 900 millivolts, and generally you have a few percent of undershoot you can have. So they spec these things. TDP is a the total dissipated power, or whatever that stands for. The TDP is somewhere in the however many 100 watts, but that's specified at a specific voltage. And so you don't want to go above that, otherwise you'll dissipate more power than you intend to, and you'll blow yourself up. And then there's an absolute max where you'll cause physical damage to the transistors. And then on the minimum side, you're talking a couple of percent, so like 3 to 4% of undershoot from the power rating. So let's say your power rating is a volt. You can drop 30 millivolts and be okay. But if you drop more than 30 millivolts, you're hosed.
That just feels very tight. And this is all at like 300 amps.
To make it tighter, yes, we're talking about a step that is a couple hundred amps. We've designed for 300 amps, and we have, I think, on the bottom end we have. How many millivolts do we have on the bottom end? Something like 5 or 6 millivolts of buffer.
Yeah, we have like 7 millivolts of margin, I think.
Yeah.
Above the spec, which apparently is world class.
Well, part of what made this very exciting is that we were also we're not using the same power controller that everyone else is using. We're using actually the same part that we're using in Gimlet, the RA229 618. And it's a good / scary sign when your vendor's like, we're really excited to see if this works. And you're like, no, if this works, it would be great. You're like, if this
you're saying if a lot, right?
You're saying if a lot, right? It's like, no, this is important human experimentation.
That's literally what they said. Like, they told us that we were the first to try this design, and while it all works in theory, we were going to put the theory to the test.
They said everybody else just copies the reference design, which used, I think, Infineon
Yes.
parts.
Yeah.
So like these are Infineon controllers, and basically the way these parts work is there's all kinds of highly proprietary ways of tweaking their control loops to make them happy. This isn't a traditional just PID controller and you go about your merry way. This is a nonlinear control. There's all sorts of crazy things they have in there. And apparently with the Infineon parts, and maybe this is just their experience or whatever, but it's kind of they send the app engineer out and they tune the thing for you. And they spend like a week in the lab and they twiddle their little bits here and there and things get better and magically your stuff's done, but you really have no idea what the hell just happened. like what's going into the chip, how it's being programmed, what those are doing, whatever. Renaissance, bless their hearts, they have a fantastic guide that shows you here are all the different control loop parameters you have access to. Here is what each of them does on an example design. If you go up, this is what it looks like. If you go down, this is what it looks like. Here's kind of the order you want to tune things in. And so with that very, very clear guide, I was able to get that thing tuned in within a couple days into, 7 millivolts of margin, which was fantastic. And so it was really nice.
It was amazing. And so it's also, this might be a good time too, Eric, to talk about the load slammer. We had mentioned the SDLE when we were talking about the bringing up the SP3 on the Gimlet, but the load slammer was really important here. Maybe you want to explain what that is and how we used it.
Yeah. So with a chip like this, you don't just, plug the thing in and go YOLO and hit power on. Because even if you were able to do that, you still have to have software to like turn the thing on and have it do intelligent things and provide clocks and all that other crap. So there's a whole lot of, things that build up to actually getting it to pull real power other than static transistor leakage. So ahead of time, what we did is we got a load slammer adapter. The load slammer is a company and they make electronic loads for industry. And they have this little module that you can plug in that'll do like 500 amps in, some absurd time, like 170 nanoseconds or something, if the voltage is right. And caveat, asterisk. But basically, you have this fake load that you put on, just like the SDLE in an AMD design or the Intel version of that. You plug this fake load in, and you get it to basically simulate a load transient like the worst case the chip would ever do. And you want to go above and beyond that, because even if you could just plug the chip in and turn it on and say, hey, here you go, let's go, you can't go above what the chip will pull. And you also can't test other VID set points, because based on process variations, you might want to run each of these chips at slightly different voltages. And so the load slammer or something similar to it allows you to test the entire power delivery network before you ever power on actual silicon. And this is done heavily in ASIC designs, especially like first article silicon designs. You want to make sure that your PDN is good and happy before you plug in your Rev A0 silicon into it, because you don't want to blow up your babies, and you want to make sure that the PDN can't be blamed for anything. As the power engineer, you want to make sure that you are blameless and nobody ever calls you up and goes, hey, I see something funny happening. And so these kinds of devices allow you to test that. But to do that, you also have to have an adapter, because the part is a 4,000 pin BGA, and you have to create an adapter. So there's an adapter that's designed for this, and it has some connectors on it. But the thing that was kind of challenging is, frankly, I didn't want to spend another, however many, $10,000 or whatever on two of these load slammers in parallel, because these are meant to be transient devices. They're not meant to be steady state load. So they have very low average power capability. And so you want some average power. And I think a couple of pictures in Arian's Twitter thread, they have this adapter that has a bunch of extra connectors on it. And so I made some adapters to go from that using literally sheets of copper and some phenolic. I got some from McMastercar and some 3M VHB, and cut all those up and bolted 4-gauge battery cables to them, to our electronic loads, to provide the DC load of 300 and some amps, and then have the load slammer provide the 300 amp step load on top of that.
So, Eric, I'm going to interject. When you do these 300 amp step loads, you're actually seeing the cables bounce, right?
I didn't realize.
That's amazing. Yeah. So, and these are car battery cables that we're seeing in that picture.
Yeah, so they're actually from a car audio company. They're New Concepts, KNUKONTEPZ or something. They have the most hilarious spelling ever. But these are car audio enthusiasts, and they just happen to have the most reasonably priced ultra high flex, high strand count 4-gauge battery cables that I've ever been able to find. So they're good quality. But yeah, even without the load slammer doing its crazy fast transients, just the static chroma load we have, I can make the cables jump visibly.
And yeah, they literally hop. They like bump on the bench.
Oh, okay. So, what makes them hop? What is that?
The transient magnetic field.
Yeah, it's a magnetic field effect.
Each other.
Wow.
Either it attracts or opposes each other depending on what you're doing.
Wow. And so the load slammer, it should be said, this is just to be clear, has replaced the Tofino on these select boards.
Yep.
So we have got, and this is not socketed. So these boards are going to be, we've got the 2 load slammer boards. They will always be load slammer boards. And if we blow those up, we don't have a load slammer. And similarly, we don't have a way of putting a load slammer on a Tofino board. So these are totally the same board design, but with a different part in them.
Yeah, they're purpose-built for this.
And so we get the boards. Eric, you start doing your tuning, which seemed like it was just going like pretty well straight out of the chute. Things were going pretty smoothly, it seemed.
Yeah, so Renaissance, like a lot of companies, they have simulation models, and the tool we use is called Simplus, and it's basically a way of approximating a real spice simulation that's still pretty accurate and is super fast for things like switch power supplies. And so I had initial tuning parameters from that simulation from running on my computer. So that is what allowed me to get basically a head start to say, okay, this is kind of where I want to start, and it'll at least be somewhat stable, and then we'll go from there. And then it was just going through that tuning guide and sitting there and blasting it a bunch. We did run into one quirk where we kept seeing things that weren't real, which was interesting.
And you were able to do this completely parallelized. You've got basically one of these load slammer boards. You've gone off to do this. And then, Arian, you had taken, I think you didn't have an actual Tofino on that first board we were using, right? That was also still a load slammer board.
No, it was the other load slammer board. So he and Matt were working on the other one, getting the management network stuff run on.
So Arian, so we're talking about that, and then we, in terms of all the things we needed to do, all the other things on this. We've obviously got the main event, but we now got Eric is off tuning and getting ready for what will be the main event. What were some of the other things we had to go do to bring this thing up?
Yeah, so Aaron and I worked on. So there's an FPGA that controls most of the. That is actively controlling most of the pieces on this board, that actively controls the enables and resets on most of the parts. The intent here is that we can more or less reboot all pieces of software without the ASIC losing the ability to continue switching packets. We can't update the ASIC, so no switching table updates can happen for a very brief period of time. But at least the ASIC can continue switching packets, which is kind of important. So yeah, Aaron and I were working on RTL for the FPGA to be able to properly sequence the power rails that are enabling Tofino, as well as some of the power rails for. There's a secondary switch ASIC on this board that provides our management network. And there's a clock generator and a bunch of auxiliary pieces that need to work. So all those had to be turned on and configured properly before we could even start to power on an actual Tofino ASIC. So we were working on that in parallel. And then as soon as that board was freed up, Matt then was able to take over and use that for some work on the secondary switch ASIC that he has been working on for the past months.
Well, and before Matt arrived, in the as we are we got to get to how
Matt arrived the second week, so we were already a week in at that point. That's right.
We were already a week in, and I feel we have to talk about South 0 versus South 1 versus South 2, and the how TOML actually resulted in us depopping a bunch of components.
Well, so we are trying to configure so there's a pretty fancy clock generator on this board that, given an appropriate system crystal and then a very high precision oscillator, will generate the required frequencies for all the components within jitter specifications. There's potentially all these qualifications that you might want to hit for use, for example, in 5G networks, or if you're part of a 5G radio network, or other applications where you have to meet these particular jitter properties. And so we have this very nice part that will more or less let us program time however we need. We can arbitrarily put things in the same time domain or in a separate time domain, meaning that clocks are guaranteed to be fixed in phase with each other or not. They can drift separate from each other. It's a very nice programmable part, but it needs to be programmed over I2C, and it was pretty much the first thing we needed after power was online on board. And so we are here desperately trying to connect to this part, and for some reason we can't find it on the bus, and we keep twiddling different things. Like, did we get the address wrong? We're scanning the bus. We're looking at the schematic, trying to piece some things together. And ultimately, we realized that I think we got the silk screen wrong, and so we're plugged into the wrong bus with the wrong header, and the part was out on a different bus, so it was never going to answer to us. And so but we've gone at that point. We've gone through and desoldered most of the components on the bus because we were wondering if maybe the bus was I think the bus was stuck in reset, or the bus was being pulled on.
Well, that one had the LPC on it, or the lattice part on there, and it was like weak pull downs, which was surprising.
Oh, yeah, the FPGA was attached to that, and the FPGA in its default state, in its unconfigured state, will pull down on the lines, and so the I2C bus was being held in basically being stuck. But that was the wrong I2C bus. It was because we were looking at the wrong thing, and so we started depopping most parts. We had some resistors in line with most parts so that we could decouple devices from the bus, except for the FPGA and one other device. And so here we are doing all this surgery, and then at some point we step back and we realize, like, oh, we've been operating on the wrong bus altogether. And so, hey, like, lo and behold, we connect in the right bus, and the clock generator wakes up and it can be configured. So we spent a couple hours puzzling on that one, but
yeah. And so I guess I didn't realize that the artwork was also wrong, because I was fixated on the fact that that Hubris was talking to the wrong bus.
Oh yeah, that was the ultimate. I think the artwork may have been wrong, but the ultimate problem was we have this configuration that allow us to basically specify a device tree in our embedded operating system, and the way that file is ingested, the order in which these devices exist changes. Like, what were the details there?
Oh god, Matt, you want to talk about this one? God.
Yeah, this was a little bit before my time, but I remember seeing the aftermath. So basically, the device is configured where you say, like, here are all of the different devices on the I2C bus, here are their addresses, here are what they are, and so on. And then elsewhere in the code, you say, okay, I want to talk to device number 1 in that list using an index. And the problem was that
we don't refer to them by name.
Yeah. And so the list of devices was being sorted, and so device number 1 in that list ended up being some random other device, because at some point in the process it was stored in a sorted data structure and then spat back out in a different order. I think that's the quick version. Does that sound right?
That's right. I mean, the tables. And Adam, how much do you deal with TOML? Do you deal with TOML in?
I'm basically not at all. I kind of avoid it.
Yeah, this is probably a good way to live.
I don't know. I mean, I use JSON, which is not a better way to live. It's just a different way to live.
It's a different way to live. All of these things have got like strengths and weaknesses. Definitely TOML among them. One of the things that is really frustrating about TOML is that the table order is not stable. So you have something that looks ordered in a file, but then it will go through a B tree, and it will actually be in alphabetical order.
But does this have to do with the like quote unquote specification of this file format, or is it simply the implementation of the parser that we're using?
It is the specification, sadly, and there's an issue which we'll link to. Okay. Oh no, this has caused us no end of grief. It caused TOML end of grief. Matt, there was a very funny thing that you had quoted, which. I don't know where you found it, but a table comparing TOML to other file formats, and one of them was comparing it to an INI file, and it was like one of these yes/no kind of strength weakness kind of table. And as it's comparing TOML to like something like an INI file, which is kind of what TOML's modeled themselves off, one of the columns in the table was strongly typed. And if you were yes, strongly typed, that was considered to be a negative. That's red. And if you are not strongly typed, that's positive. And Matt had the very funny line of like, did an ini file actually write this table? I mean, but yeah, that was a frustrating issue. I feel that issue has bit us many times with TOML. I feel like, Matt, didn't it bite us like? I felt like it bit us on the spy stuff as well, not that long afterwards.
I think it did. That sounds right. I just know that the fix was just to switch to a custom deparser that was called ordered TOML, which just maintained ordered lists for all of these lists of dictionaries and so on.
Yes, that was when Cliff hit the last straw. Cliff is like, forget it,
Yes.
We're never doing this again. And I'm actually changing us over to my own thing called ordered TOML, just like TOML, except tables are ordered at the end. But anyway, so yeah, we deep. And Nathaniel, what you guys end up depopping on that? You were able to get it all back on? Obviously,
yeah.
Sorry.
Nothing was too bad. I mean, we took some series resistors out, and we might have taken a small, like 4 or 8 pin chip off. I think we took one of the temperature sensors off that we maybe didn't really need, at least on a Bringup board, and but yeah, it wasn't like massively destructive.
But we were running out of things to take off.
I mean, it wasn't. But yeah, we did get to a spot where it was like, well, it's the BGA and the processor, and there's not much we can do about either of those two things.
So anyone listening, including my future self, anytime you do a new board and you don't know what the I2C bus is actually going to end up with, make sure that you put series resistors between the bus and every device so that you can easily depop the device from the bus in case something is misbehaving.
Yes.
I did want to hop back and just tell a funny story about the first week of Bringup, which was like all power all the time, including our hotel room, because our hotel room lost power.
Right.
And so we a number of us were staying at a local hotel, and the hotel had like a main bus fault. And so, on day 2 or something, we had to leave work and go grab our stuff and move to a different hotel.
Yeah, and to be clear,
when you say have power again the rest of the week.
Right. When you say lost power, this is not like the power was out for like an hour or 2 hours. This is like the hotel no longer has the capacity to power itself.
Right. It was like a week.
They got one of the little yellow earthquake disaster stickers because the fire department told them to kick the people out. So
yeah, I tweeted that one. I tweet very little, but I tweeted that one. With the restricted use sign that says, "Yeah, this is not safe to be habiting, to be in." So yeah, that's not good. The thing that blew up is drastically bad to have blow up. It's called a bus duct, and it's it's pretty horrible to have one of those go. You're having a real bad day.
So even when we weren't at work, we were still dealing with power issues.
Right, and I'm not sure if that was a good omen or a bad omen, but that was right. I totally forgot about that, Nathaniel. So you all had to move to a different hotel in all of this, which was very disruptive. So then we are doing all power all the time, as you say. That first week went pretty smooth, and now we're. I don't think there was anything that was really. I mean, I think things again we were kind of where we wanted to be going into week 2, and now a couple things were happening. One, we were getting ready to actually bring this up on the actual Tofino. So, Eric, do you want to describe kind of what you had done with the tuning, and I mean, your confidence was growing that we could actually not blow this thing up.
Yeah, so I kept abusing it in different ways, trying to see if it would blow up, and it seemed to be behaving. And there was some noise that was happening in the load slammer because of some quirk that I still haven't figured out. But basically, we were seeing fake overshoot or undershoot that was not actually there. And so that took a couple of days to convince myself I knew what was going on. And the nasty thing about this is, you can't just measure this with a normal scope probe because ground changes when you pump 500 amps through it. Because even your ground planes, this is a 20-layer board, and we have probably 12 layers of ground, 12 or 14 layers of ground. I mean, it's stupid how many ground planes we have. But even that, will change by, 10 millivolts at 500 amps, and 10 millivolts doesn't sound like much, but when your margin, and your tire tolerance is like 30 to 40 millivolts, 10 millivolts is a big margin.
And so Eric, why is ground changing? What's causing that?
Because you have current flowing through it. So
yeah, these same electrical magnetic properties, these fields change, and therefore
it's not even fields; it's just straight resistance. I mean, ground is a wire, right?
Ah, that's true. Yeah, this is
that
resistance.
has, like, let's say, a milliohm of resistance, right, which is pretty low. You pass 500 amps through it, that's 500 millivolts of drop you'll get across it. So your ground planes have to be in the micro ohm range, and the PDN actually is in the range of like 200 micro ohms. But
200 micro ohms. Sorry, I'm just okay.
200 micro ohms up to like some megahertz.
Wow.
To be able to meet the voltage tolerances.
Eric, what is it? How much resistive power are we burning in just the copper layers to supply 500 amps? It's something like 40 watts?
Yeah, somewhere around 40 or 50 watts.
So there's 40 or 50 watts dissipated through the PCB just because of the resistance of the copper as you deliver power from the power FETs through the ASIC.
Wow. And the resistant properties of that material, we're in the domain of material science with that.
Yeah,
is that
just
right?
The resistance of copper.
Copper. Okay.
You're running into fundamental limits of and that's why these chips all implement remote sense, where they remotely sense both the power and the ground. So they measure the voltage differential at the load with all these high power controllers and these high power chips. And so because you can't use a normal scope probe for this, you have to use a differential probe, but many differential probes are limited in their ability to measure with low noise. And again, when you have tens of millivolts of margin, noise is important, and so is DC offset and all these other things. And there's like one differential scope probe that apparently can do this, and I didn't have it at the time. Because we're a startup and I don't have $1 million of test equipment lying around that we've built up over the last 2 decades. So it's so it's it was challenging, but it's like, okay, I measure the voltage drop, and I measure how much the voltage changes on the scope probes when I do different DC load levels to see how much ground balance I have. And I figured out that, okay, yes, I'm seeing this and it's fake, and I don't have to worry about it, and so then I can trust the results, ignoring these couple of little quirks, which are also not physically possible. So it's not like I was just trying to ignore something that was not pleasant. The quirks we were seeing were not physically possible. So,
and were they not physically? How were they not physically possible? It's like
so usually when you have a load step, like meaning load is added, your voltage drops. But in this case, the voltage was rising on a load step, and it was dropping on a load release, and that's not what happens.
Right.
And the way we proved this to ourselves is we also dead shorted the inputs to this thing. To the device that was actually measuring this.
Okay.
And even when it's measuring ground from both inputs, it saw the same spikes. And so there must have been some sort of either external coupling mechanism because of where we had to run cables on the load, near the device. And you can see it's fairly crowded. So it was either something like that, where there was some sort of magnetic field coupling in there or something, or there was just, some other quirk that we just didn't understand. But basically, it was measuring noise, and we proved to ourselves that, yes, it was noise, and we can ignore it safely. And then once that was settled, which took a while for me to convince myself of that, it was basically, okay, you have the main rail, you have a few aux rails, which are, only 80 amps or 100 amps or something. There's little piddly ones.
These little small rails, right? Exactly.
Yeah, these little small rails that take like 3 90 amp multi-phase controllers. And so once I kind of worked through all of those, I'm like, yeah, okay, I'm reasonably happy with all these results. And there's a nice spreadsheet that Intel had provided about the rail tolerances and things, and I filled that out and I checked every VID, so every voltage that it could run at, made sure they were all happy and none of them were weird or anything. And I was like, okay, well, Arian, Now what? What do you want me to do?
Well, and Eric, I think it was about like I remember one of the metaphors you had for this is like you have to understand this is like jumping out of a plane and landing on a tightrope that is made of like dental floss. I mean, that is like how and I just feel like as if I'm like, okay, I'm like, wow, this is going to be definitely holding our breath for that. And the way these things, you don't necessarily pick the timing of some of this stuff. And Steve, do you want to talk about the fact that we had a potential investor who had a previously scheduled time to come visit us while we were going to be powering this thing on for the first time?
Yeah, I mean, we were at our office. This was as we were starting to get back to where one might have folks in a well-ventilated office, and so had a prospective investor up here, having a meeting with them, and it was when we had the hardware engineering team in town to do Bringup on the Switch, to which we had not yet gotten to a happy place, and. In the midst of the meeting, all of a sudden, all the white lab coats abruptly kind of got up and huddled around the board and with like furrowed brows and were, kind of turning and talking to each other in muffled voices, and which made it impossible for me to do anything other than crane my neck the entire time, which made the rest of the meeting very awkward. After the fact, of course, it was revealed that that was a planned event from the engineering team to prank us as we were sitting over there talking to said investor.
Because come on, this is the birth of this is the birth of a little machine over here. It's kind of rude to invite the outsiders.
I mean, fair.
It's a family-only event.
Yeah, right. Very, very well deserved. I mean, I have all the respect in the world for the prank. It didn't make the moment any less uncomfortable for all involved, but yeah.
Well, and in particular for Steve, I have to say that like I was just like, look, like whatever's happening over there is happening over there. We're going to have this conversation, and then there'll be plenty of time to weep tonight. I don't need to weep right now. Steve is like trying to read body language. I'm like, no, don't. What are you doing? Just like anyway, definitely, it was a very effective prank. And I mean, the good news is that I mean, Eric, I'm sure you were holding your breath, but I mean, stuck the landing when we powered it up.
Yeah, I was terrified. I don't know how many more hairs I lost off my head that day, but that's why I shaved my head. So I don't.
For the listeners, Eric is bald.
Yeah, well, I'm not totally bald. I shaved my head, but I accept the fact that I'm going bald. I own it. So, but yeah, it was one of those like, oh man, I hope they don't regret hiring me.
I hope this works.
Fair.
Power Up was really uneventful because we put the heatsink on, and
the heatsink was.
It was like, all right, we're plugging in this board. We have tested the power up sequence. We know that the rails are powering up in the right order. All the timing is correct.
Can we just talk about the heatsink for a second?
Yeah, that thing's like 8 pounds.
It's pretty awesome.
It's an the whole bottom of that thing is a vapor chamber. So like, if people know like a normal heatsink, you'll see those copper pipes coming up, and those are heat pipes, and they have like water usually in them, and the water evaporates and it moves to somewhere else, and then it condenses and flows back to the heat source and everything. The entire bottom plate of that heatsink is one giant vapor chamber, which is the only way in hell you can move that much heat over that big of a space in any effective manner.
And it's got to be, what is it? I mean, it's 9-10 inches. Sorry to use imperial here, but I mean it's or more.
It's
if you're looking
millimeters wide.
Yeah, if you're looking at the pictures on the board, if you look at where some of these pictures of the adapter that I showed in that thread that we were talking about earlier, there's an outline there, like a large rectangle around this whole thing. That's the outline of the heatsink. This thing is almost as wide as the board is wide, and it is about 1.5 inches tall, and
we had one of our Adam. Did you have any insight into the moment arm crisis? One of the
The moment ARM crisis?
Yeah, exactly. So one of the early concerns, we got a very partner doing Mechie work for us, very good partner, and they had one of their concerns was the heatsink was going to be so large and so heavy that you've got the moment arm, which is to say the mechanically the force that would be necessary at the very edge of the heatsink to crack the PCB would be scarily slight, and you get very nervous about the thing actually.
No, not crack the PCB, crack the die of the chip. Because in transport the heatsink might vibrate, as it undergoes, like as a thing is transported, and those vibrations will cause the far outsides of the heatsink to potentially rock back and forth ever so slightly, but this is an exposed die device. There's no heat spreader, there's no protection whatsoever, and so if you apply just enough force on the edge of those little dies, then you might crack them off, and therefore, who knows what happens then.
And fortunately, this is changing the heatsink from copper to aluminum, right, Arjen? That was like the big win in terms of being able to pull it in a little bit.
So the biggest, so the thing we at some point settled on, initially we weren't looking for a vapor chamber design because it was slightly more complicated, slightly more expensive, and lead times were longer on that because it's just a more involved manufacturing process. Well, we did eventually settle on a vapor chamber, and then what we could do, this is a while ago, but basically the fins are the fins are aluminum, so we're using a copper base with a vapor chamber and an aluminum fins, and the fins heat travels only so far into those fins, and basically initially the design was taller than it needed to be. Basically, simulation showed that the amount of heat that would reach the very tip of the fins was rather minimal, so we could easily shave off, I don't know, I would say 10 millimeters or 15 millimeters of the fins at the top, like from the top, basically, and that alone cost a significant reduction in weight, something like 400 grams, I think. So that brought us down into the sort of 2.5 kilogram range, which was where the mechanical engineers were like, okay, we're okay with 2.5 kilograms. We can sufficiently support the heatsink on both sides to make sure that it won't ever rock far enough that it will cause enough force on the die to be a problem.
But it is a big heatsink.
It's a very big heatsink. It's a very chunky boy. And soon your graphics card coming to your PC near you will have equally large heatsinks. The next generation of GPUs are dissipating about, like, TDPs are in the same ballpark, and there's a real knee in the curve. Once you go past sort of 350 watts, things become that much more difficult to cool. You need more air velocity, etc., and so everything becomes much more difficult. So it will be interesting to see what future GPUs, high-end GPUs, will look like, because those are going to be very beefy pieces of metal too.
Yeah, and of course we're all air cooled, so that's the other kind of factor here that you can. But I would expect most GPUs. Oh, I actually shouldn't say that. I'm sure gamers are all water cooled now. So we get this thing. You get it. Flip the switch, and then Eric, are you pretty happy? What are you monitoring when you let current flow through that thing for the first time? What were you monitoring to ascertain whether we had achieved success or not?
So at this point, it was mostly just making sure the voltage was right versus the VID of the part we were using.
Got it. Yeah. Okay.
I wasn't really concerned about the load part of it anymore, because I was watching the input power and the load monitor on the Renaissance chip, and it wasn't like there wasn't that much load coming from it because a lot of stuff was still in reset. But most of the concern at that point was, okay, is the heatsink working? Is it getting warm? Because if it's not, then our chip is going to self-immolate and desolder. So watching and making sure, it's in Kapton tape to, because the whole heatsink is like nickel plated or whatever. So it's very shiny, and it doesn't work well with thermal cameras, but you put some Kapton on it and it gets it reasonable enough that you can see if it's getting toasty. So we had some Kapton on it, and it you take a thermal camera and point it at a really shiny surface like metal, you'll just see the reflection of whatever it's pointed at.
Oh, I didn't realize that. So I think I missed the fact that you've done that for the thermal imaging.
And I think Aaron put a picture of the heatsink with the Kapton on it in reply to the Twitter Space thread.
Yeah, and it's pinned in this if it shows up for you, although it doesn't seem to show up for everybody.
Yeah, it shows up for me. But yeah, so we put some Kapton on that, and that's a close enough approximation that it at least gives you some reasonable assertion of the temperature of the heatsink. And once I saw that was like getting a little warm in the middle, and warm meaning like 2 or 3 degrees above ambient, because the heatsink's a beast. And at this point, there's no like screaming fans blowing at this thing. It's like some little puny desk fan that's propped up in the background.
That puny desk fan is actually
that moves quite
a bit of
air. Exactly.
But they've been doing pretty well. Compared to the self-levitating double-stacked fans that'll run, as fast as a jet engine. Yeah, no.
Yeah, but they're like 9-inch fans. The diameter of those fans are great.
It is. It's a legit diameter.
And then is this where you is this 2 to 3 degrees above ambient? Is this what you call puppy dog warm? I know you refer to puppy dog warm. No. I haven't figured out what puppy dog warm is yet. I just know that
it wasn't even puppy dog warm at that point. But once we let the thing out of reset, then it started getting like puppy dog warm, which is like a few more degrees above ambient. It's basically like puppy dog warm to me is like if you pet a dog that has not super thick hair, super long hair, like a puppy. If you pet a puppy, you feel kind of that general like cozy, comforting warmth from the dog. That's puppy dog warm.
All right,
so I feel like a great term of art here.
Yeah, when I feel like I never got all I got from Eric is like, that's puppy dog warm. That's not puppy dog warm. This is not yet puppy dog warm. So I'm trying to figure out what exactly puppy dog warm is.
Do you need him to put it in cat terms for you, Brian?
It's quite literal. It's happy kitty warm.
Thank you. Yeah, if you could just convert it to cat for me, that would be a lot easier.
This is black cat in the window in the sun for warm. This is
There you go. So we like what this part is doing. And now maybe it's actually a good time to kind of like we've got that working. Maybe Matt, you want to talk about what you were doing, because this is not actually one switch; it's actually 2. And you were working on getting the other switch up during this time. You want to talk about some of the things that you've done with that and some of the things you'd found?
Yeah, definitely. So like Brian said, the main sidecar, the switchboard, actually has a second lesser network switch on there, where by lesser network switch, I mean a 54-port, 80 gigabits of switching fabric switch. So like much heftier than anything you would use in a consumer device. And the purpose of this switch is to run what's called the management network, which is the network of all of the service processors, which are equivalent to baseboard management controllers. So this is very low level. It comes out of reset kind of before the main switch, and its job is to shuffle packets around. And it needs to be pretty dumb. Like all we really need is for packets to go in and go out and some amount of VLANs to kind of tune where they go. But you can't buy
Matt, sorry to interrupt.
Port. Yeah.
Matt, sorry to interject, but just to tie it together for other folks who have listened, these service processors are where we're running Hubris, just to complete the picture a little bit. Sorry, Matt, go ahead.
Yeah, definitely. And so it turns out that you can't buy a dumb 54-port 80 gigabit switch. Like no one sells that because that's a really weird thing to want. And so instead you get to buy a very fancy, like this is meant for your light home network or light server rack switches with 800-page data sheets and 800,000 line SDKs to work with. And so bringing that up was very exciting because the data sheet, despite being 800 pages long, doesn't actually tell you everything you need to do to bring it up. And so there was a lot of reverse engineering the SDK and kind of tracing through it to see what it's writing and looking at all of the secret bonus registers that exist in the SDK but not in the data sheet to get this thing actually up and running.
And this is the VSE 7448 is the chip here, and I would say the vendor here is like many of ours, which is like not unfriendly, but also made it very clear that we are not on their well-trodden path. They're just like
Yeah, what is this SDK? Is this some like that they expect you to have like be running Linux somewhere?
Yeah, so the chip
Actually,
is
yes.
interesting because
Yes.
it is a switch in that it's got a bunch of switching fabric, but it is also a MIPS processor in there. And so you can strap some RAM and flash to this switch and boot up Linux running on the same chip as the switch.
Wow.
Which is kind of
awesome.
Their happy path. Like that's kind of what they expect you to do. That's what their dev kit does. That's kind of the most common use for this chip.
That's right. And so this is a MIPS core. Adam, if you're wondering where we had MIPS in the product, it's this MIPS core that we actually can't use because it's not attached to any memory.
Yeah, we didn't attach
like
the DRAM.
True 64 or anything on there.
No. But the result is that we've now been told, after Matt and I have asked several rounds of questions about, hey, how is this supposed to work, or how, like, we're not seeing X or Y happening. They've now told us, like, listen, you need to use the SDK or not bother us with any questions at this point. So fortunately, we've made good progress, and Matt has made good progress, and we're through, I think, arguably the critical sections, and we were probably able to do it from this end on our own. But yeah, it's definitely been an adventure.
It was definitely an adventure, and Matt, you had gotten us a dev board for this thing, and I'm used to these dev boards being, I don't know, like something you can hold in one hand. And your dev board, of course, it's a 54 port switch. I mean, it's a huge thing that you've got to go develop.
Oh yeah, it's like probably like 1 foot by 2 foot, and is shielded on both sides by like 1/4 inch acrylic plates. It is
it's more or less a translucent rack mountable thing. It's 19 inches wide, exactly. It actually could go into a rack, I think, if you were to put mounting ears on it.
And so, Matt, and you had basically, before we brought the stuff up, you had managed to talk that thing directly via SPI from hubris running on I think on the Gimlet, right?
Yeah, exactly. Because we don't want to be using the internal MIPS processor, you can strap pins and cause it to boot up without that processor running, and then it acts as a SPI device. And so we had a separate microcontroller that was talking to it over SPI and just writing hundreds of registers on startup to bring the switch up, with a mix of documented and undocumented settings. Like some of the surveys in particular, the things which actually send stuff down the line, are just blobs of cryptic configuration that they don't really tell you what they do.
And is this where the hidden 8051 was not, or the not so hidden 8051 was not in this part, or was this one have 8051s? I mean, I'm sure there are 8051s everywhere. Why am I?
The secret 8051s are in the PHYs, which are a separate chip, but it goes through this chip to talk to the PHYs. So yeah, one of the things we discovered is that the SDK includes sets of code to configure very specific PHY chips. Like if you have this PHY, you need to apply a patch, which is this array of binary numbers, to the 8051 core running inside the PHY, because of course that's a thing.
And then, so Matt, somewhere along the line, I was trying to remember where it was in that week. We've got the 7448, then you've got these additional PHYs that you need to go talk to. And if I recall correctly, you were able to speak to one of the 8552s, but not the other. Am I remembering that right?
I'm not sure. That doesn't sound like what I remember.
This is the thing that ended up being yet again the slew rate.
Oh yes, so that was we could talk to one of the PHYs that was configured one way, but one of the other PHYs, which we configured through a different interface, was refusing to talk. And I'm sure Brian remembers this because I worked on this for an entire day. I told Brian I was going to go home, and I'm sure that I would solve it first thing the next morning. And sure enough, I go home and relaxing in the hotel room, I think to myself, well, we've already had 2 issues where the microcontroller slew rate on pins has caused things not to work. Where you get to pick. So when you're configuring a microcontroller pin, you can say, I would like this pin to be slow or medium or fast or very fast. And of course, everyone picks very fast because, like, why would you pick anything but the fastest possible slew rate? I can hear all of the other like electrical and analog engineers wincing in the background here. And so sure enough, these pins were configured as very fast. And if I came in the next morning, the first thing I did was I changed them to slow, and the chip immediately came up. And Brian came in, and I told him it was working now. And he looked at me like, what did you do?
Well, and in particular, because you've just been so like, well, this doesn't work, but I'm going to go home. I'm going to sleep on it. I'm going to come in. I'm going to fix it. I'm like, wow, okay, all right. Well, that sounds like that's a good plan, I guess. That sounds like you know what's going on. Then that was great. I was very impressed. I also have to say, you've been bit by this issue a couple of times. I got bit by this issue on the slew rate. So, Adam, have you been? Did you get any?
No, I'm not read into this one at all. So
when you configure these GPIO pins, just as Matt says, you've got these. What you are configuring is how quickly it rises or how quickly it falls. And as Matt says, it's like your options go from very fast to slow. And so you're writing software, you're like, obviously, yes, I want very fast, of course. Like, why would I want the slow one? It's like, well, you want the slow one because if you raise the level very, very quickly, you are much more likely to get signal bounce. Or rather, you have to pay attention to how things are terminated, because the signal now is this like abrupt, sharp edge, and it's likely to bounce off when it hits an impedance mismatch. And I'm doubly correct me if I'm wrong. I'm sure this is like I'm butchering this explanation, but you'll get this reflection back. And when you're talking over like SPI, so you start literally hearing yourself if you're talking over SPI. And as a software engineer, this makes you want to cry, because you see like rampant data corruption, but not total data corruption. It's like, I can see that like this thing is trying to do the right thing some of the time, and then for reasons that but then it does the wrong thing a lot of the time, and it can be really, really frustrating.
Yeah, what you effectively get is you get this ringing behavior where it takes a while for the signal to settle, because you get these reflections that are basically rattling back and forth between all your parts, especially if you have a bus that has multiple drops and then there's a header that is unterminated. So all that stuff starts reflecting back in all directions effectively. So it will take a little bit of time to settle. And if your part is either sampling at the wrong time or your controller is sampling at the wrong time, then it might be sampling, at the trough of one of those oscillating like as it bounces, and yeah, you will read a 0 or a 1 depending on where that is at that point.
It's cruel.
The other fun part about this is that if you attach a logic analyzer, you'll be adding a little bit of capacitance to these lines, and that is often enough to make the problem go away.
And that might make it go away, because that will provide just enough termination effectively to make these rattles be a little bit less violent, and therefore they will settle quicker and things will get happier.
And Adam, it's funny because obviously we've talked about
the setting. How do we change the setting? Like what? It's just, Matt, you're just literally changing a line of code.
Oh yeah,
from fast to slow.
Yeah,
that's awesome.
You can add a capacitor.
I mean, it's basically setting a register in in the processor somewhere that tells it what to do.
And we would love to have different nomenclature for this. It would be great to go from like safe to dangerous. It feels like people would not be using dangerous unless they knew what they were doing, but it goes from fast. It goes from slow to fast, and everyone picks fast, and you actually want to be like slow or medium. You want to be you want that rate.
Slew rate is as slow as you can get away with.
That's right. That's as slow as you can get away with is what you want, and you want to default to be slow, not fast.
Yeah, the slow slew rate works for like a 40 megahertz SPI connection, so it's not slow. It's just not the fastest possible.
Right. But Matt, you were through that week making really good progress, getting we had a PLL failing to lock. I remember that issue. I know that you got it resolved, but I don't know what was the resolution on that one.
I think that was just one of the like gazillion configuration registers you had to bring up exactly right in the right order. And what I ended up doing was compiling the SDK on my desktop, and replacing all of its register reads and writes with calls that would actually print what it was doing. So
that's awesome,
the SDK, it would pretend to configure the chip on my desktop, and then I would just read through every register write and compare that against what I was running to see if it matched. And sure enough, there was one of them that was different, and that was the problem.
Oh man, that's funny. I didn't realize you'd done that. Yeah, well, that was great, and a great find. And then we end up at the end of this 2 weeks. And Arjen, we are right on the cusp of being able to bring this thing. I know you really wanted to get this thing all the way up to talk PCIe at the end of that 2 weeks, but we we weren't quite there. We were super, super close, but we weren't quite there. But I thought we were ahead of where we wanted to be. I don't know, Nathaniel, what do you think?
I think we need to talk about the load-bearing dongle right at the end.
Oh, yeah. Please, go ahead.
So, I mean, we had, over the course of this 2 weeks, for whatever reason, we basically had 2 FTDI dongles that we were using to program these the FPGAs, and we only had 2, and one of them I had brought with me, and so as we got these boards in different places, we have people running these dongles back and forth, because every time the board power cycles, we have to reload these images, and so we're getting ready to pack up. And like I'm packing up my dongle, and then everybody's just looking at me like, you're gonna shut the company down by taking the dongle home.
Right. That dongle, the entire company is in that dongle. And I think Aryan had already I recall running out to get Aryan before he left, so we could get the second dongle.
Aryan had left, and I think he came back to drop off an extra dongle.
The second load bearing dongle. That's right.
Steve, did you drive me back to the office? What happened there? I know that or I drove back to the office, maybe, or we all drove back to the office. Yeah, but anyway, for the listeners, we had parts. We just hadn't had the time to solder more dongles together so that we could use them. This was all happening rather quickly, and those things quickly fall by the wayside. But yeah, we now have sufficient dongles for the company.
And so now we are going into, but I thought we were right where we wanted to be in terms of we had managed.
We managed to not flame one of these boards, and because we only had a couple, and so that would have been a real setback. So hey, stuff's still working. No magic smoke has been released. So and the PDN is running. So that seems good, which was good.
And we're getting, we talked about the spy wiggles and Nathaniel's spy wiggles on the SP3 and how those initial spy wiggles were kind of that initial sign of life. And we've got something similar here, right, Aryan, where we've got the Tofino is going to be loading its configuration from an attached EEPROM, and we're seeing that sign of life.
Correct. So Nathaniel posted some pictures on the thread, the space thread, mentioning U35. U35 is a little spy EEPROM where there's a bunch of parameters that the SerDes IP in the Tofino ASIC needs in order to configure its PCI Express link, which will then, once PCI Express is up, you can then configure the rest of the ASIC. Everything goes over PCI Express. We messed up the footprint, so that was one. Nathaniel had to do some surgery there to get us to get a part in place that we happen to have. But then getting that to program was a little bit of a thing where there we run again into the problem of slew rate being too fast. So here I sit at a table on the last Friday of Bringup, frantically trying to get an external programmer to work programming one of these little EEPROMs so that we can get these parameters in there, solder, get it to the board, and then fire up this thing. Because without these parameters, the PCI Express link is never going to come up. And so we get stumped again by this slew rate being too fast, bit errors happening, and I could program this thing, once out of I could program some pages reliable, and then some pages would not be reliable. And so after a day of work, I was about to jump off the bridge almost, and both Brian and Steve talked me off the ledge, and they were like, "You go home," and Brian was going to go and fix this over the weekend. Which he ultimately got, but I think it even cost you still.
It definitely, absolutely. No, I got nailed by this thing as well. So it definitely was. It was more painful than I thought it was going to be. But we got to the point where we could and what we're doing is taking this kind of binary payload from Intel that describes in a format that I don't think we've got any visibility into that format, right? Aryan, this is its little goober that's going to describe how it configures the PCI links. And we got it programmed that next week, and I definitely felt like it was Aryan, I think you and I were both joking that we're taking this little astronaut and kind of programming this little ROM and then kind of sending it off into the rocket to go. This little tiny EEPROM has got all the information that's going to be necessary for this fire-breathing monster that Eric has configured to actually work properly.
Well, actually, so when we powered it on, I should what we first saw after we had some headers so that we could look at the waveforms. But so as the device powered on and we let it go out of reset, the first thing we see is that hey, it's starting to fetch it's trying to figure out what kind of EEPROM is there, and then trying to read the configuration. There was no configured configuration in the EEPROM, but at least the part was showing signs of life. Like the clocks were running and it was doing stuff over SPI. So that's where we left off, probably Thursday. And so we knew that the part at least had come out of reset and was doing something, and it was and it was up to us to deliver these parameters through the SPI-ROM to bring them up to then get PCI Express to work. So yeah, that took us about 2 weeks to get to, from boards in hand, not knowing what to expect, to powered up and ready to go and explore, get this part to work.
And I felt like, I mean, obviously, Nathaniel and Eric, I defer to, Matt, I defer to your expertise, but I felt like that's about as smooth as that was going to. I mean, I felt like that was not going to be a lot faster than that. That was about as smooth as it's going to get.
I think like one way to gauge that, especially relative to Gimlet, was just our MCN process, which is just it's almost like capturing our bugs in hardware and things that we need to fix. For the next round, I was just looking in Gimlet. We created 42 bugs, hardware bugs, and on Sidecar we have 6.
Yeah,
which just shows that we really cleaned up our process a lot.
Yeah, we did. I mean, and huge kudos to you, Arjen, and to the rest of the team. And we got better, which was great. I think that was very, very gratifying, and I thought that went pretty smooth. And then, Arjen, going into that next week, everyone kind of leaves Emeryville, and it's kind of like, I feel like everyone kind of leaves everyone comes out for the birth, baby's alive, everyone leaves, and now it's Arjen is now left with this this 3-week-old that we need to kind of like begin to get to the next stage, which is getting it to talk over PCI. So do you want to talk about the I mean, the contraption, the kind of how would we get this thing to talk over PCI, and your eBay score on that?
Yeah. So, long story short, or what I referred to earlier, this thing is connected over PCI Express to an external cable, but that is not a standard cable in any way. This is part of our custom cable backplane that we're developing for this rack. And so there's no off-the-shelf cables you can buy for this. And so we had some, we basically cobbled together what I love to refer to as the contraption, using an adapter board that would let us break out the individual conductors, like the twin X conductors, effectively into SMA cables, so that we could rig up basically a cable that would go from the connector underneath the board to a regular PCI Express slot on a consumer motherboard, because we did not have the compute sled ready to be connected to this thing yet, because we could not run enough software on that just yet, and so we needed a more ready to go PCI Express host, and so we put together a small motherboard with just an off-the-shelf AMD client part, and a 5600X, I think. And we used a PCI Express test card from the PCI Express SIG organization that you can use for link validation, that happens to have SMA connectors SMTP connectors, SMPT connectors, and we then jumped that through the breakout board, and then into the custom cable that goes underneath Sidecar. At this point, we have replaced that we have made a little adapter that will take our custom cable and pin out to a regular SEM slot, so that we don't need that anymore. But as
did you literally get this on eBay?
No. So as we were working through this, we were running into some. Basically, the link wouldn't come up, and so where do we start debugging this? Because now we're talking about a PCIe Gen 3 link, 8 gigatransfers per second per lane, and high speed clocks, and now you need serious measurement equipment to go and figure out what's wrong. Fortunately, my bad eBay, like late at night test equipment buying habits led me to hoard some of this stuff, and we happen to have a PCI Express analyzer and a PCI Express exerciser, an older model from LaCroix, but we happen to miss a crucial cable for this thing, and the cable is still current, and LaCroix will not sell it to me, won't sell me a used one of this. They tried to charge me $7,000 for a new one, which was a little bit out of the question. But it so happened that we managed to score a one of these cards that goes with these devices that came with a cable for only $1,600. So we got the cable. So we bought the adapter card for the cable, and then with the cable in hand, which arrived like 1 or 2 days later, we managed to get we figured out that at least the PCI Express lanes were connected correctly, and the clock was connected correctly, because the analyzer. Or the exerciser could connect to this board.
And this thing, and Arnie, did you drop in a photo of this thing in your Twitter thread? I mean, this thing is true Frankenstein. I mean, this is like you got a third of it bought on eBay. I mean, the thing is like this is and when it was not working, Arian, you had a very clear idea of what you thought was going wrong.
Yeah, so I don't know. I have a picture, and I posted a picture at some point. But the problem is, if I close the Twitter app, I don't know.
No worries.
Thing will drop.
So
I will post the picture later. But yes, because when I started digging a little bit, and what I realized was that there's several different clocking modes for PCI Express, and we were assuming that both these systems could be independently clocked, which is a supported mode, but which is not the default mode. Most PCI Express configurations are what's called source clocked, which means that the root port or the root system will also provide the source clock by which all the cards or PCI Express devices are clocked. They will use that as their input to synchronize their SerDes directly. So there's no clock recovery going on. They basically just simply take that clock input. There's a transfer function in order to determine how you need to change your phase relative to that clock, and then you start sampling bits. And then when implemented correctly, that will cause the bits to be sampled correctly and the link to work.
Could you just expand a little bit on what clock recovery is?
So clock recovery is the process of so a lot of these high-speed serial links like PCI Express or SATA or SAS or Ethernet now too, instead of sending a clock along with the data as a separate signal, that at these really high data rates, that becomes now you need to make sure that the clock and data stay in phase and so that causes that causes some challenges, because you need to make sure that that the clock never either leads or trails your data, but is right there within that exact window where then the sink is going to use that clock to capture the data. A link that, for example, does do this is to some degree is HDMI, where a clock is sent along, which is used for recovery of the sample point. And so instead, PCI Express relies on can rely, if you're not using this source clock mechanism, you can rely on clock recovery, which means that you're using the data stream to embed the clock. You're using certain character transitions in the data stream to happen such that you can recover the clock. You're using certain symbols that have certain bit patterns, effectively, that you then use to train a PLL so that you can recover the clock and then sample appropriately. But for like most client PCs that just have PCI Express slots in which you insert, your graphics card or your networking card or whatever it is, any PCI Express card, assume more or less that these are source clocked systems, and so the AMD CPU or your Intel CPU will provide, or the board itself will provide a clock to these cards, and the cards, the chips on these cards will align themselves directly. If you do not want to do that, you need to turn on there's two different modes that you can use for PCI Express, where you can say, both systems have an independent clock, and now the chips both need to recover these clocks. If you don't set that appropriately, the clock recovery functionality of these links will basically not be enabled. It will be bypassed, and now you need to, and then if that is not enabled, what you're then going to have is that your data is going to be out of sync. The clocks are going to be out of sync between these two systems.
And I mean, fair to say, it's rather unusual to have a PCI device that's much larger than the host, which is the case for Sidecar.
Yeah, this is not a regular, like normally a directly plugged in device. This is not a problem. So the solution here was that we also had to send the clock through the external PCI Express cable to Sidecar, which we had accounted for. The cable included a diff pair to do that. But we needed to configure the clock generator that I was talking about earlier in the space to basically generate an appropriate PCI Express clock from the received clock that we got from the host, and once that was in phase, the link would come up. The analyzer was not as picky in the analyzer the exerciser rather that we attached to the system with that cable and the card that we bought from eBay. That one doesn't really care, and it just oversamples and then figures out where the clock needs to be, and it will still work. But your regular AMD client system will not. So once I figured out that this was simply a clock being out of phase, the fix was fairly simple.
How did you figure that out? Was that just by kind of Godonkin experiment and knowing?
I had a hunch that might be the issue, and then start to look for some documentation. There's some good PCI Express reference material out there, including a clock chip, basically a datasheet for a clock chip from Renesas, which describes these different scenarios and why these different things work the way they work. And so, armed with that, I had a pretty good sense that this was a thing that we should explore. And once we did that and figured it out, it was pretty quick.
Yeah, I mean, once you did that, and that was indeed the issue. Once you did that, we were able to actually talk to it over PCI, which was an exciting moment.
Yeah, and because once you get that working, it means that you can now get the 1 million plus line SDK from Intel to go and configure the rest of the chip. Because this chip is there's no way that you can do this without their help. There's so much logic and functionality going on in this thing that you are solely beholden to what the software that is provided for something like this. This would take a long time to rebuild if you wanted to write that from scratch, because you need to know how these ASICs work, work.
The route that we're taking, that Matt was able to take with the VSE 7448, is just not practical. With Tofino's,
over time, we still want to probably write a lot of this stuff ourselves, because there's a lot in the SDK because this ASIC is designed for for a variety of different rack switch configurations and sort of rack switch deployments, and they are targeting Sonic, for example, as the operating system for this thing very clearly. And there's a lot of functionality in the SDK that we don't necessarily need. There's a lot of dynamic configuration ability that we are not going to be using, and so there might be some. Over time, we might start to cut out some of these pieces, and maybe only rely on the lowest level C library that they provide to interact with the ASIC, and then build up functionality over time on top, because we still because it's like a pretty large chunk of C++ that is difficult to understand.
So while we're doing this, we kind of hit the end of January. We made great progress there. We maybe need to back up a little bit and now talk about Gimlet, because Gimlet's now happening in parallel, and we've hit a couple of stumbling blocks with Gimlet in January that are proving pretty frustrating about the same time. Nathaniel, do you want to talk about I'm not sure if Robert is there via his voice on Earth, Steve, but do you want to talk about some of the things that we were hitting with the T6? I know in our case here too, actually.
Yeah, so the T6, we have a PCIe connection on the board that's soldered to the Gimlet with the Milan processor. And so, pretty quickly after we got power sequencing set up there, we were able to start communicating over PCIe with that thing, I think, right? I think we were talking, well, I guess. No. We thought we were at one point in time, but as we went through it, provably we weren't. And it's there's not that much stuff for that chip. I mean, it's got a few strapping options and a big PCIe lane.
And that thing is not wanting to come out of reset. RFK,
for context, this is the NIC in this server sled.
In the server sled.
And just to be really clear, like very important. Like we need this thing to work.
Yes, our company does not exist if this doesn't work, right? So this is the dual 100 gig NIC, and there's a lot of software that we have created to get access to the PCIe stuff, and so like Robert has done a great job like untwisting all of the like deep details on the Milan's PCIe cores and everything, but we have a lot of software that like hasn't been totally checked out in here. And then in addition to this, we were struggling to get this chip to respond the way we expected it to over PCIe.
Well, and in particular, this thing is just not coming out of reset.
Yeah.
And RFK, we pulled up the clock, and it was pretty clear that the clock could use some improvement.
Sure, it could be better.
And then we got it better, and then it did not come out of reset.
Well, okay, it got
a bunch
better,
of problems.
But like RFK and I were out there in February, and it was like, I mean, we basically off-boarded the chip. I mean, off-boarded the clock to our own clock generator, and we used so we desoldered and hacked on SMAs, and because the clock was looking bad. It turns out, after going back through it, we realized that due to the part shortage, we had dual stuffed oscillators to have options, and both of them were actually still stuffed and were driving the PLL chip, and that was making the PLL chip a little bit unhappy.
Wait. So Nathaniel, does this mean we had both parts on the board so that if we weren't able to source one, we'd be able to just but it's always intended to sort of be half populated, right?
Correct. We only need one of the two possible oscillators we can use here. However,
and we need exactly one.
We need exactly one and no more.
That's right.
And as we went through bomb generation for the board, something got lost in translation, and we ended up actually both buying and soldering in both circuits, in addition to the like optional resistor that connects both of them. So we had two 50 megahertz clocks or whatever trying to drive the clock chip, and it turns out that the PLL, does some like clock cleaning, and it's like kind of good, but it gets a little bit mad when its one input has two clocks.
You get some non-monotonicity in your signal, and it just won't go away.
Right.
And you can like try to change the termination around and stuff, and it just like doesn't stop, and it's very strange because it looks like termination issues, just like impedance mismatches, but turns out that that's incorrect. And I'm shocked the thing works at all with two clocks.
Well, and so we probably spent a good like 2 days or more chasing that down.
Right.
Well, to the point of like you had said, like basically we removed everything and and jacked in an external clock, bought a clock generator that didn't get there in time. So we used a dev board of the same chip that is on the board in order to get the new signal, piped in the best clock possible. We're sure it was going to work, fired it up, and it failed, which was really sad.
It failed exactly the same way that it did 2 days before.
Information available from this large effort. Excellent.
When I feel like this was it was such a flashback to the SP3, where it's like we just could not get this thing to come out of reset. And
less power this time.
Exactly. That's right. Well, and that's right. Talking about the Eye of Sauron. Well, and we don't know what this thing is, and it's like, and Nathaniel, who come out to Emeryville for the Sidecar Bringup. I mean, poor RFK used doing all this because all these hypotheses take time. And so RFK is sitting there reworking this thing over and over and over again. Nathaniel's like, I'm going to go out there just to help him. And that was that the first week of February, Nathaniel? Yeah. And we are going through absolutely everything in this part. Chelsea is being helpful, but on the other hand, we're hearing, we've never seen this before. It's like, oh shit, this again. But why is this thing not coming out of reset? And exploring, we got Nathaniel, you were out for that week, and I think that you came out with confidence that you and RFK were going to get that nailed in that week, and Robert would get that nailed.
Yeah, I mean, I thought between three of us focused on that issue for 5 days, or most of 5 days, we would there are only so many things, and I mean, on Friday, as I had to go catch the train, like it was kind of sad because it was like, oh, we didn't, like, we're no different than when I came out on Monday, and I mean, we know a lot of things that it isn't. Right. And we've made a lot of improvements and found various problems, but none of them have really like moved the needle. And then like I had to go on vacation, so I was like, headed home and then like out of the office for the next week.
Oh, and Nathaniel, I liked it at the end of the week. You're like, well, in conclusion, this thing should be coming out of reset.
That's right. I demand it to be so.
Right. And then I feel it was about this time that maybe that next week, because I think on the end, again, I'm not sure if Steve and Robert are there, but Arian, you back to Sidecar, you have the big breakthrough of actually getting this thing talking over Gen 3 in the middle of that week. Like I think that the 11th is the date that sticks in my head.
I think that I was on the train and I got chatted that Arian had made a big breakthrough, I think. So like that happened that Friday, I feel like.
That Friday. Okay, yeah. But it was
I waited until Nathaniel was gone, and that's when I turned it on.
There you go. Nice.
That's the asshole I am.
But I just remember getting, like, we now have this very sophisticated part in terms of the Tofino that is now we're doing really well. And I think it was then, Arian, that I just remember really shouting at the T6. It felt really good actually to shout at the T6, to be like, everybody is here. T6. We've got like the SP3 is here, Tofino is here, we've got the management network here. We've now brought all these parts out of reset, and this fucking Nick just will not come out of reset.
And then I step into the picture where everyone has been working on it really hard, and I've been watching from the sidelines.
Well, Rick, I was
what's going on and watching all the work.
I was going to walk us up to that by saying, you and I are having a conversation about this. I am feeling down. I am like, in part because Nathaniel, very optimistic engineer, Nathaniel's like, in conclusion, I have no fucking idea what's going on. And so, Rick, you and I are talking, and Rick, I just remember you being like, we'll get there. We're going to figure this out. And I'm like, I'm really not sure that's the case. I am really like, I want to believe you, but Rick, you were very, you're like, look, we'll get there. And then I think, Rick, with that teed up.
And thankfully, Rick has a history of modifying off-the-shelf boards to help us out.
Yes. So because, Rick, you're
right. So
like Rick has an ethanol that's missing like 30% of its bomb and still boots.
Right. And so that was the same thing here. As I had a couple of T6 add-in cards that I had used for a variety of early experimentation. So I don't mind modifying them and seeing what happens. And with this, taking the same approach. Okay, so we have a design that we made that we've been hacking on and trying to get working. We can't figure out why it won't start. So there's a whole lot of things it could be, and it's sure we can spend a lot of time trying each of those, but we're not. You're kind of rolling the dice as to, can I guess which thing it actually is that's wrong? And so I took the opposite approach. I took a known working board and just started modifying it to be closer and closer and closer to our reference design, or to our actual design, until it broke. And in this case, it took, I think, 3 tries. And it was really, some informed guesses. We had looked at a lot of things already, so I knew which areas to look at. I had talked with Chelsea and had some ideas of why we might see the behavior we did. And it turns out that there's some strap resistors. So essentially you have some resistors that pull a pin to either ground or VCC to set some initial configuration. And a couple of those on the T6 choose which clock source to use. And this is really important because it's the clock source that's used for a very, very, very early startup of the chip. So the very first thing it should do is go through this hardware-based sequence of loading some configuration out of a SPI ROM and then actually starting up. And then you should see some output on pins. And we weren't seeing this happen. And so that's why we were focusing on clocks so much, is we thought, oh, it's just got to be, the quality of the clock going in is not good enough. Well, I changed the resistor from the value that was on the add-in card, which was suspiciously small at 500 ohms. And I put in what we have listed in our BOM for our design, which is 10K ohm, and it doesn't work.
It doesn't work in the same way that ours does not work.
Exactly the same way. And so I typed this into chat, and I think it was pretty late because, like you said, Brian, I had talked with you at like 3:30 p.m. Pacific time. And then I went and did this, and it was, 4:30 or something. People were mostly done for the day. And I say, so I changed this, and it broke. So there's a very quick rush to go take one of our Gimlet boards to change out these resistors to 500 ohm to see what happens. And sure enough, it works.
And the thing that's kind of shocking about this is, Rick, it is 10K on the schematic, but RFK, you had already changed that to a 1K resistor.
We have changed these probably 6-7 times to 1Ks, which should work. Based on the IBM specification of the I/O of the die, that should be fine.
That should be fine. And Rick, you had said that if you had known that there were 1Ks on there, this is an experiment that you might not have done.
Right, because this was being that these are pull downs. You'd expect that they don't have a lot of current draw in them, and you can run fairly high values. And that's where it being 500 ohm in the official Chelsea reference design seemed odd, but yeah, I probably wouldn't have tried it had I known they had already tried 1K.
But changing that into a 499 actually worked. And Steve, I don't know if you and Robert are there, but if you got some retelling of when that thing came out of reset, I believe. Unfortunately, I was physically out of the office. I had to go take a call, but there was some exuberation when that thing came out of reset.
Yeah, there was definitely some exuberation. There was also, I think I recall, and by the way, Robert had to depart, unfortunately. So the value coming from this speaker drops way off at this point in the narration. But I remember coming back into the office and a couple of loud expletives that erupted from the folks that have been working hard at work on this one, and just like kind of just that unbridled joy when you've been just banging away at something for so long and not seeing a clear path to resolution and then nailing it. And it was a very exciting moment.
I believe Robert was screaming, "We're going to live, we're going to live, we're going to live," over and over again. Is that correct?
Yeah, there was definitely an expletive in the middle of that, but yeah, definitely.
That's right. Yeah. And Frey, fucking 500 ohm resistor.
And like, that's one of those things. I mean, I'll remember where I was on vacation and I saw that come through chat and was like bouncing off the walls. And, but one of the takeaways is like, for a bunch of experienced people looking at this stuff, like you just look at pull-up resistors and say, oh yeah, we have the pull-ups, but like we really should have gotten on there and probed voltage measurements, because that would have told us pretty clearly that we weren't getting pulled where we thought we were getting pulled.
Yeah, definitely. I mean, that would have been like, even little stuff like that, especially when you're working with vendors where they don't really build all their own IP, right? So they're getting this stuff from IBM or they're getting, wherever, and they're implementing it and it's working in their system. And they're going to go over it about as much as they say, hey, this works and it's in the specification for the requirements that we have for our product, and it's fine. So they're not going to make sure that it's nice for you. And probing all these things is pretty critical, because you're going to get weird stuff like this, and it's going to go on your top 10 list of most bullshit things that you've had to deal with.
Well, and I also felt it was very vindicating, Rick, of your approach, which you had taken on Gimlet as well. it had yielded an ethanol X that was like missing many of its parts and still somehow booting. So it was still like valuable information. But this approach of starting from kind of the other end with something that was working and trying to get it closer to the thing that's not working really paid dividends here. So that was a very big breakthrough. And it was kind of a relief to, I mean, on the one hand, yes, we should have, I mean, obviously done those voltage measurements, Nathaniel, but on the other hand, like, pretty surprising that pull down has to be that strong, that a 1K was actually not sufficient.
Right. That certainly is like not kind of what you expect when you see parts with pull downs. And so I think like that's sort of why, it was easy to gloss over as we looked at it.
So with that T6 at a reset, that was a big breakthrough. Another thing that we kind of hit along the way, and I know Robert is off, but and I'm not sure if Rick is still here or not, but the footprint issue we had, Nathaniel, where Rick had done the rework. I don't know, when did that?
Just gonna say,
other
things that you don't expect to be wrong is where pin 1 is on various packages.
Yeah. So we had, I mean, this would have been probably, this was before Christmas, I think, that we determined this, because I think our PCB guy did that kind of as a project over Christmas break. But,
right, I guess that did a lot earlier. Right.
But we had so we have these like 16 pin DFN packages, so they're kind of like a little QFN, and like various things, we have this whole complicated hot plug logic network with, things go through some AND gates and some inverters and that kind of thing. And, like in late November, early December, Robert and I are on the phone talking, and, he's measuring stuff on his board, and it's like, the input to the chip, it looks like a shorted output. And, I'm looking at the board I've got here, and I'm like, yep, no, I can confirm that doesn't look right.
That's bad.
Right. And so then, then it's like, okay, well, something's got to be wrong, because like this, there should be an output and an input, and you can't get, in the middle somewhere. And so, looking at the footprint, looking at our CAD, I realized that our CAD had been built with basically the pin numbers all rotated by a single pin around the chip. And so, and the way a lot of these parts work is, you'll have like an input and next to an output, next to a ground, next to a power. And so when you rotate them, you just get a huge mess in your net list. And so, we had realized that. And so, after we realized that, it's kind of like, well, what do you do? Because that's kind of like the parts are smallish. They're, they're not unreworkable, but like this is probably not something we want to do 12 times on our fleet.
You say small-ish. To any normal human, they are extraordinarily small. So you describe like the actual size.
I mean,
these are small.
The size. The chip is like smaller than your pinky fingernail. So, and there's 16 pins in that space.
I was going to go like it is getting into like grain of rice territory.
Well, it's bigger.
It's a DFN.
It's a DFN, so it's bigger than that. But it's small, and the problem with DFNs, especially like when you're just playing around in your home lab, is that there's not much for a lead there because they're kind of leadless, and so it's tough to do anything with them. And then given the issue that we had, it wasn't like we had to fly a pin or something. It's like we need to rotate by one pin, which like your square little DFN basically can't do that. And
so Rick volunteered to rework this.
Yes. We can let him talk about what he did. I think he posted a Twitter picture too.
I mean, some context, right? So this is a bunch of discrete logic gates that are used to do some complicated logic around the signals from a PCI edge card, like a normal plug-in card slot. But in our case, it's a little different because we know what's being plugged into there. And so we've changed some of the meaning of these signals, and we want to detect certain situations. So it was important that we actually validate that the logic worked correctly before we cut the next revision of the board. So we couldn't just, say, oh, well, we'll fix the footprint and then in the next revision, we'll actually test the logic. Like we needed to actually validate that how we thought this worked actually worked correctly, and that would work with the AMD processor, because it has a lot of assumptions about how the PCIe hot plug signaling works. So I volunteered. I have enough of a rework station at home that I could do this. And then they told me how many of these footprints were on a board. So
I think it was like 12.
Well, because the same footprint was used for a variety of these discrete logic gates, it ended up being like 12 or 13 footprints. And I'm like, okay, so how bad is that? Well, these are, I forget what they were, like QFN.
16.
Huh?
16.
16 pins. So 16 pins times 12 packages. You're talking a lot of pins, and these are pretty small pitch.
These are super small pitch. Adam, I think if you could, next time you're in the office, you got to see this thing physically. This is like nuts to me. I mean, I know this is like by reworking standards, this is merely like workably small, not unworkably small, but this is really fine work.
And that's why when I say have a reasonable rework setup, like I have a microscope. I have, a fine pitch soldering iron and tweezers and all the setup. And I'm not set up to do really, really small things, but this was I can probably make it happen. Now, for people who are not familiar with this, like I'm using 32 gauge wire, and that's big for what I was doing. So I set to work. I went through and removed all of these chips because they were all, as Nathaniel pointed out, they were doing things like shorting outputs to inputs and various other things. So I wanted to remove them all just to eliminate any sort of unintended behavior. And then I was like, no, there's no way I'm going to be able to sit here and solder individual wires, because I have to actually... What I'm doing is taking the chip and flipping it over on its back and hot gluing that to the PCB.
You're dead bugging them, right?
This is literally what they call dead bugging, because it looks like a dead bug, right? You squished it against the back of the PCB with its legs up in the air. And so now I have to attach wires to each pin on the chip and run that over to the correct pad on the PCB to fix this mistake. And yeah, the prospect of doing that 16 times on 12 chips was not good. So I started with one, and that took about 20 to 30 minutes to do one chip. And that was a lot.
Yeah, man.
So I went back to the schematics and figured out, okay, if I just want to make one of the PCIe slots work so I can test this, how many chips do I have to do? 4. Okay. I can do 4 chips. 4 chips is somewhat reasonable. 3.5 hours later, I had been staring through the microscope the whole time, doing reworks. And part of the problem is that as you get further and further in, you have denser and denser wiring. You have wires overlapping. And so as you're working on something, you'll bump a previous one, and that's just enough tension, like you didn't get a good enough soldering joint, so it'll break free, or you'll melt one wire by accident when you're working on another one. So yeah, 3.5 hours of microscope work later, I had it all reworked for these 4 chips so that I could test that the hot plug circuitry worked the way we thought it did. And it turns out it does.
This is great.
For the most part. There is one quirk that we had to go back and rework, which is, important. Had we not tested this, we would have built revision B incorrectly. So it was important work to do, but this is the time, like, for all that we talk about the time spent on things like the pull-up resistor, where you're trying to understand what the problem is. And it's actually, the fix is really trivial once you get down to it. It's the hard part is figuring out what the problem is. In this case, the problem was really obvious.
Right.
It was just the sheer amount of effort required to do the rework that takes all the time.
Rick, this is heroic. I posted what I think is your picture of one of these chips. But one of my questions is, so how did the schematic get into OrCAD or whatever incorrectly?
So this is one of those scenarios where you have to verify everything, because actually the schematic is correct. So if you look at the schematic and you look at the part data sheet, everything matches. And like, I was wrong. This is actually a 14 pin part, not a 16, but it's 4 millimeters square. So like, this is not a big part. But yeah,
that is a big grain of rice. I'd like to say that is in grain of rice. I feel I can find a 4 millimeter square grain of rice. Sorry, go ahead.
So the symbol that we drew for the schematic was correct, but when the layout person built the footprint for it, where they started their pin 1 was actually on pin 2 or maybe on pin 14, depending on, I don't remember which way it was rotated. And so what happens in that case then is what we think is electrically 1 and what the chip thinks is electrically 1 ends up actually being electrically pin 2. And so it's just like a human error mismatch between the schematic symbol that we drew and how the part is actually manufactured. And you build all of these manually kind of off a data sheet. And, for a lot of parts, there are rules of thumb, but in this case, it was just a human error that messed that up. But so that's how you get the mismatch.
And it's kind of amazing that it doesn't happen more frequently. I mean, Nathaniel, you had made this point with Gimlet that about how lucky we had been in so many different dimensions, and lucky that this didn't happen more frequently, honestly.
Yeah, well, most of our schematic symbols and footprints have all been like created as part of this company and by various people. So we had some partners helping us with some of those, and then we now have some of that in-house now. And so a lot of this has been like kind of created by a bunch of different people. And a little tiny error where you just happen to miss where pin 1 is can have devastating effects. And as we go through and mature our library process, there will be more reviews and more people looking at this stuff, so that there's kind of a double check, because like these kinds of pins can be this kind of a problem can be very expensive. And these are like popcorn logic parts, and so we did a lot of looking at the T6, and we did a lot of looking at the ARM, and we did a lot of looking at the SP3, but like in this case, this was just missed. So. But we've had very few of these, so we can be thankful for that, and our library process is getting better as well.
It is, and we got lucky, and then on this issue, I mean, again, heroic rework from Rec to at least allow us to validate the design, because what we were trying to do in this kind of parallel to bringing up Sidecar is we're trying to get the design for Gimlet completely verified, and I'm trying. Are there other mishaps? I mean, I feel like we hit most of the Gimlet mishaps here. Nathaniel, am I missing a glaring one?
No, I think that was most of them. And and then on Sidecar, I mean, I posted a picture in the Twitter thread about we had like the wrong package called out, so like we bought the wrong parts that didn't fit the footprint, so that was the flash part that I reworked on there. But we haven't had any anything that was like that crazy of a miss from data sheet to to implementation. I think on Gimlet we had we had to use some copper tape and beef up some power rails in a couple of places. So that was a little bit nasty in a certain manner of speaking, but Eric did nice work there.
Management network, that was a good one.
Yeah, the management network had some polarity swapping and some other issues, and I mean like TX and RX swapping, because some of the parts have kind of a sad symbol naming.
Yeah, but there we managed to do it wrong twice, both on the connector end and on the chip's end. Right. And so and then we fixed the chip end, and then we were wondering why the link still wasn't working, and then we realized we had to reverse the connector end now too. So yeah, that was a fun one too. Shit.
A very double fault.
Yeah, exactly. And then, Arnie, do you want to talk about kind of the latest update on Sidecar? So things you got PCI up from a configuration perspective. Mm-hmm. Kind of the last major piece on Sidecar was actually like, okay, did the links work at all?
Yeah. So with some software running now, we've been working on a switch management piece that can program tables and program the P4 program into the ASIC and bring the links up. And we recently managed to get some links working loopbacked on themselves. So one port of Tofino to another port of Tofino. Those links that we in several different configurations, ranging from a short little loopback cable to cables that are representative of the backplane that we intend to ship with. And we managed to close the link at the intended or the possible 400 gig that each Tofino port can provide. So but
do you want to mention some of the hurdles we had getting there? Because I think they're both kind of representative and interesting. At least two of the ones I can think of.
Yeah. Also, as Niels and I are debugging this, and we're can't get the link up, we think we have all the code right, and so we enlist Intel's help. We set up a meeting so that they bring out some of their engineers of their team. 10 minutes prior to that meeting, I'm like, oh, let me make sure that the setup is correct. Like as we are prepping for that meeting, and I lift up the board and I realized that we actually removed the loopback cable between the two ports because we were going to do some VNA measurements on another board with that same cable. And we did the measurements, and then I never put the cable back. So I was like, okay, this is one reason why this port is never going to work. Like this was not intended to be a wireless thing. This was intended to be wired. So I stick the cable back, and luckily it still didn't work. So I was like, okay, fine. Like at least we didn't waste 2 weeks of time on just a stupid cable that we just forgot. And for the context here, these cables are under the board, under this metal chassis that is visible in some of these pictures. It's very difficult to see that there's no cable under there. So.
Right. Just
in all the chaos.
In your defense a little bit. Yeah, exactly.
That was missed. So here we go into this call with some Intel engineers, and we walk through various pieces, and then we turn on. We had configured the BSP for the platform for these two ports, and couldn't get, even in test mode, we couldn't get a single wiggle on one of these links. And so we're going back and forth, checking a couple of things. And it's like, well, we don't know. So what we advise you to go and do is maybe we just have the wrong ports here for some reason, because the way this is driven in their SDK is there's this long spreadsheet that you take, and then hardware the SerDes engineers basically fill out properties of the SerDes in this spreadsheet, and then there's a Python script that then takes the spreadsheet, basically the comma separated values of the spreadsheet, and then turn it into this JSON blob that then goes into their SDK. And then from that, they distill a port configuration that they then load into the device. So it's a multi-step process. We skipped a bunch of these pieces because the JSON parser broke for us. So we basically built a couple of C structures that represented the port configuration for what we were doing. So as we are debugging, we found a couple of small issues, like when we were put the port in test mode, you do need to give it analog tuning parameters, meaning these SerDes are fairly complex pieces that require that can basically there's tuning parameters that you need to load into these things, and without tuning parameters, the ports are never going to work. So you need at least something. So as we were on the call, one of their engineers pulls off out of one of their running systems existing tuning parameters that they found that would work for a 50 centimeter or 1 meter cable. So that would be in the ballpark of what the cable that we were working with. So first of all, we needed to set those. We hadn't set them properly. But so then as we were working, the port still doesn't work, and we go through this process, and they're like, well, you need to go and work out, you need to basically build your entire platform. You need to load all the ports into your platform so that if we, for some reason, have two ports connected to the wrong thing, then you just try them all, and at some point one of them should start working because they're connected to each other. So at some point you should see something. I was like, okay, fine, we can go do that work because but that was representative of a couple hours that we needed to do. So we couldn't do that right on the call. And as we were talking, one of our engineers says, "Oh, you know what? Let's check the port numbers because I remember there's a mismatch between the port numbers that we use on the schematic symbol and the port numbers that are used in the spreadsheet." And as it turns out, the schematic ports are labeled 0 through 31. And the ports in the spreadsheet are labeled 1 through 32. And so the ports that we had configured were off by 1. And so after we changed the off by 1 error in our code and restarted the process, lo and behold, the ports worked, and the link came up, and we were underway. So it was as if we hadn't plugged the cable in, but then the cable was in the configuration was assuming the wrong port. So for those of us in software wondering about the off by one errors, it's off by one errors all the way down to hardware.
That's right. Yeah, off by one. I mean, and what a brutal. I mean, it obviously feels very vindicating to get that nailed, but also felt you're just like, oh my god, it's all off by one errors. And
yeah, but the thing was that we should have had that call with them just a little bit sooner, because while we didn't waste huge amounts of time, because it wasn't a 2-week full-time effort. We simply would have missed a couple of things. Like first of all, the off by one error we would have not have known, because they were using the exact same labels that they used on the pins of the device, like the device symbol, and how they talk about it in the hardware guide. They use the exact same naming convention except in software, except then in software everything was off by one. We would have never figured that out, I think, by ourselves. Well, maybe not never, but that would have been a long one.
Yeah.
And then the transmitter parameters is something that I sort of knew about, but it didn't really click so much. And
it should be said that when we have been making all of the decisions about what parts to use, a part of our calculus is figuring out what a partner is going to be like to work with when things don't work. And we've been really blessed. We've got some folks that are very, very invested in helping us figure this stuff out. I mean, in some ways, like the thing I felt best about on the T6 was Chelsea's certainty that like we will get this resolved. Like, okay, this is good. You're not gonna. Ultimately, we figured it out, but they were definitely as perplexed as we were on the T6 issue, and always available to brainstorm.
They get some serious props. Their guy that we're talking with, Jeff. He's like the FAE that will take a phone call from his customer while he's at dinner with his wife.
They were really, and which was great.
I don't know if we should encourage that behavior, but it's nice that he does.
That behavior. Do not do that.
Yeah,
do not do that for anybody. That is not like, you don't have to do that. But it's like just dedicated. Could not. We were having so much trouble, and he was gonna do anything.
Yeah,
it was incredible.
It was deeply appreciated. I feel the same way about, I think Intel's been great on the Tofino side too, about really, and AMD too, when we had the SP3 challenges. I mean, we've really turned to these folks, and we tend to do our homework. So we tend to be, tend to show up having the common stuff nailed, but
like the cables plugged in.
The cables plugged, exactly. That's right. We make sure the cables plugged in.
Yeah.
But yeah, so we, in the end, I feel like we've done our EVT, our revision B for EVT has taped. Nathaniel, what boards arrive in a couple weeks, right?
Yeah, they are somewhere between where the actual PWBs are been shipped to our manufacturer. So
that's really exciting. Really expect, I'm going to knock on wood, but we really do expect that Bringup to be pretty smooth. I feel we've got a lot of experience now with this thing.
We fixed a lot of things.
We fixed a lot of things, and we touched a lot of the board, but we fixed a lot of stuff.
And we also start with code and a level of things that just exist that did not exist on day one. First time.
We have so much more debug software for all pieces in the system now.
We do, and I feel like that's been something that's been fun, is to get that debugging software better and better. And I feel like, I mean, it helped us in Sidecar. We were faster on Sidecar than we were on Gimlet because we had, I thought, learned a lot from what we wanted to have in Gimlet. And I feel like we've made it better yet again for Rev B here. So it's been fun. I mean, I think that's kind of borne out a lot of the certainly our belief in the hardware software co-design.
Yeah, and we're using a lot of the same parts on a lot of these designs. So, like, one thing we didn't talk about, like, Sidecar had we had a missing capacitor on a couple of power supplies, but we had caught that issue in a design review for another design, like 2 weeks before Bringup or a week before Bringup, and so that was all fresh in our minds. So as we're going through troubleshooting, why a power supply didn't turn on, it turns out that required capacitor is required. And so, but that helps as we start building a bank of functional circuits and stuff parts we're comfortable with and parts we have good references. That really helps speed things up as well.
Yeah, I think we officially go from ripping up all Extant designs we go from part of the solution to part of the problem in terms of like, no, don't change this stuff, it works. You can certainly see why people have that bias, but yes, building up that all that shared knowledge is very helpful. Anything from anyone else? Any kind of parting thoughts? Or I know we've gone on for. Adam, thank you for the extended time here. I knew this was going to be a long one. We had a lot to talk
I was
about.
fired up. I knew it was going to be at least 2 hours. Yeah.
And hopefully this delivered. It's been a wild couple of months here, but and definitely some terrifying moments. I do feel, boy, it was darkest right before the dawn though, because I was in that conversation where Rick is like assuring me that we're going to find it. I was really not feeling optimistic. So a good object lesson there too, in terms of just retaining that resolve and that perseverance. And then also, honestly, I feel on all of these things, I don't know how you all feel about this, but I think it is really important to have a team of people attacking these problems where different ideas, different perspectives, people trying different things has been really essential for us.
Yeah, I 100% agree. I think, it's so easy to get lost in the forest, and you need someone else to, come back out and say, hey, look, like Rick did with the part, like, I'm going to go play, in this other space. Or, we've had lots of those where it's like somebody has an idea, and because, the rest of us maybe get buried in a spot, it's that external perspective that really helps unlock things.
Yeah, it's been an advantage too of being a bit distributed, honestly. I mean, I think a lot of people have asked, how do you do a hardware company as a distributed company and a remote company? And, honestly, like that was a good example where I think it really helped that Rick was not in the same room as like RFK, Robert, and me, for example, where I think that like the body, like it was good to have like a little bit of isolation there and being willing to do different kinds of experiments.
He's not tainted by our
exactly.
Well, and it forces conversations into these like common channels where other people can kind of opt in and opt out as they want rather than needing to be in the room. You just have to be paying attention to a certain chat channel or something. You can always scroll back.
Yeah, and that has been really, and certainly as I was going into this space, just trying to remember everything, it was very helpful to be able to go through the chat channels and the party hat emojis. We definitely use the party hat when things work. It's nice that you can go back and search the party hats.
We're missing the party parrot.
We're missing. That's right. That's right. Yeah, we're not fully Slackified, but we got the party hats. All right. Well, I know it's late on the East Coast in Central Time, but thank you everyone for joining us. This has been a lot of fun to get these tales down. Arjen, thank you and Arjen, Eric, Nathaniel, Aaron, Rick, RFK. Thank you very much for Steve and Robert. It's been a lot of fun to actually record these, and I really enjoyed listening to our past episodes to remind myself of the problems. But it's gonna be fun to carry this one to the future as well.
20 years from now, we will all reminisce about the one recording we did with the nicks and the switches, and yes, it will be cool.
It'll be good. The 500 ohms, man. The 500 ohms that saved the company. That would
trauma.
It's totally
trauma. You force relive the trauma. Good stuff.
All right. Thanks, everyone. See you next time.
Thanks.